Hey, welcome back to Graph Theory. In this lecture, we're going to wrap up our work in Chapter 6 on graph colorings. And in this section 6.2, we're going to be taking a look at the kind of edge analog of our vertex coloring problem, edge colorings. All right, so you can see the goals of the lecture there. We'll kind of walk through them together and then get started. I guess I'll say as kind of a disclaimer up front that I'm going to treat this material pretty lightly. I want to show you some of the techniques people use to prove stuff like this. There's a couple of theorems below in the lecture, but we won't delve into this quite as deeply as we did for vertex coloring because I want to move on after this lecture. We have 6 more lectures in this class, and I want to show you some results about a class of graphs called planar graphs, and hopefully kind of accumulate with a very famous theorem in graph theory about coloring maps. But anyway, that's in the future. Let's get back to what we're talking about today. So you can see the goals of the lecture. What I want to do is motivate with an example and introduce and define what I mean by an edge coloring of a graph. And then edge coloring will have a so-called edge chromatic number, and I want to establish a couple of bounds for that. One of them we'll give a proof of. The other one I'm just going to cite a theorem for. And then I want to do some calculations, show you some techniques of how people think about stuff like this. We'll compute the edge chromatic number of complete bipartite graphs and complete graphs. And then we'll kind of end by just sort of surveying some known results. There's actually, in terms of computational complexity, there's a lot of active research in this business. So I'll just give you a couple of results that are known, and then I'll just encourage you, if you're interested in this, you can contact me, and I can point you to some links or some other places where you can read about what people are actively kind of working on in this area of mathematics. All right, so let's motivate it with an example. Let me carefully scroll here for a second. So here's my motivational example. Suppose that you have some league. I said arcade, a little league. It can be anything you want. These edge coloring problems kind of come up in the same context as colorings, vertex colorings, but it's typically when you're sort of trying to pair things. So here is my example. So I have this little league, 5 teams. They have fancy names like A, B, C, D, and E, and I want each pair of teams to play a game. Right, so I want team A to play team B, C, D, and E, and so on. I want everybody to play each other once. They play at most 1 game per week. Okay, well, there's 5 teams in the league, so every team is going to play 4 games. And the question is, well, what's the shortest season? How many weeks does it take in order to have these 4 teams, or excuse me, 5 teams play a game when they're playing once per week? So we can model the problem with a graph. You can see it over there. I'm going to model it by letting the teams represent the vertices in the graph. I've labeled them A, B, C, and D there. And then I want edges to be representing a game. So for example, this edge between A and B just represents when A will play B. This edge represents when B will play E, and so on. So I want all teams to play every other team. So it's a complete graph. It's a complete graph on 5 vertices. But now how to come about this idea of how many weeks is it going to take? So I'm going to introduce a new notion. I'm going to color an edge in that graph that represents a week of the schedule. So let me just scroll down a little bit. And here you can kind of see I've filled it in beforehand instead of trying to coloring the edges is too slow for the video. But here's my scheme. Well, I have 5 teams. So every week, one of the teams has to sit out, right? You can't pair up 5 things, but you can pair up 4 of them. So say in week 1 that I've colored those edges red there, team A is sitting out. It has a bye week. And in week 1, team B is going to play E, and C is going to play D. All right. And then I have a second week, blue. You can see A plays C, E plays D, B sits out, and so on. So according to the way we've modeled this problem, I can just kind of change the question. Basically, I'm asking, okay, well, what is the fewest number of colors that I need in order to color the edges of that graph in such a way that no 2 edges that are incident with a given vertex have the same color, right? Because if you had, say, if A had 2 blue edges, then A is playing 2 games in week 2, in week blue. But we want each team to play at most 1 game per week, not exactly 1 game per week, but at most. So just rephrasing the question in kind of graph theoretic terms, I'm asking, what is the smallest number of colors that I can use to color the edges of that graph in such a way that no 2 incident edges get the same color? Okay, and I'm not claiming that I've proven the answer here is 5, but I've at least shown that the season doesn't have to be any more than 5, because there's a schedule that you can just see how each team sits out and how they're going to play. So you could do it in 5 weeks. A little bit later in this lecture, I'm going to try to convince you that you can't do it in 4. Even though there are only 4 vertices incident with every edge, you can't color that graph in 4. Okay, so there's the motivational example. Let's give ourselves some terminology and then we'll get to work. Okay, so we're going to call a k-edge coloring. K-edge coloring of a graph. It's a function from the edge set into a set of numbers 1 to k. I think of those numbers as colors. And there's no restriction on that. So any function from the edge set into it. A proper k-edge coloring is a k-edge coloring in which anytime 2 edges are incident, they don't get the same color, all right? The edge chromatic number is denoted by chi1. That 1 is not super visible there. It's subscript chi1 of G. The edge chromatic number, it's the smallest positive K that G admits a proper K-edge coloring, all right? So very analogous to the notion of vertex coloring. It's just that we're saying incident edges have to get different colors. Edge chromatic number is the smallest possible K. You can do that. So in our motivational example above, the Little League example, we were basically asking what's the edge chromatic number of the complete graph K5. All right, and I didn't prove it, but I guess what I proved in showing you that coloring is that thing is less than or equal to 5, right? Because I properly edge colored it with 5 colors. Cool. Okay. So first result, and it's a quickie. It's somewhat obvious. Recall that the notation capital delta of G just denotes the max vertex degree in a graph. So the edge chromatic number is certainly going to have to be greater than or equal to that. Yeah, because if you have a vertex of degree delta G, well, there's delta G edges incident with that vertex, and they all have to get a distinct color. So you're never going to properly edge color a graph with less than max degree of a vertex. So in our K5 example, that delta of G was equal to 4. So it's conceivable that you could 4 color that graph, but you certainly couldn't 3 edge color it or 2 edge color it because, sorry about the scrolling, close your eyes if you don't want to get dizzy. You have a vertex with 4 edges incident to it, you need at least 4 colors. That's all this theorem says. I don't even think I wrote a proof of it. I'm just going to put it in the realm of obviousness. Let's take a look at this example. It's a hand-drawn version of a graph that's in your book, and I'd like to calculate the edge chromatic number of it. Okay, so I see vertices of degree 4 in this graph. S is one of them. Y is a vertex of degree 4, but that's the biggest vertex, a degree. So delta G of this graph is 4, so it requires at least 4 colors, right? And in fact, pick a vertex of degree 4. I picked the vertex S. So pick a vertex of degree 4. I picked this one. There are 4 edges incident with it, so it has to get at least 4 colors. We can randomly assign them. You can give them, if you want to just use number labels, it's fine, but I'm going to color them green, yellow, blue, and red. All right, so I'll show you the picture. There I have a picture of this graph G, and I've assigned 4 colors to the edges incident with S. I would have to give those 4 edges 4 different colors, and those are the 4 I chose. All right, and now proceeding, looking around, I'm going to pick on this edge VZ over here. It can't get the color red, and it can't get the color yellow, but it could get blue or green, and I have a choice. I'm going to color it blue. So I'm going to color that edge VZ blue, you can see, and now you just try to finish it. I think you should stop this video, get out a box of crayons, make a quick sketch of that little graph there, and finish it. You'll have choices. two of us doing this we might end up with different results. So do it. I'm going to move on so that the video doesn't get too long. But here's how here's one possible 4-edge coloring of that graph G. All right, so I decided to color the edge VZ blue. I could have colored it green. And then I just kind of, not too systematically, just sort of filled in, trying my best to make sure that no two edges incident with the same vertex are the same color. And I was able to achieve it with 4 colors. So you can stop the video and look at mine, or you can look at yours, but no vertex here has 2 edges of the same color incident with it. Yeah. The degree 4 vertices, of course, have all 4 colors. The smaller degree ones have less, of course. But we knew that the edge chromatic number was at least 4, and I've 4 colored it, so it's equal to 4. So that graph has an edge chromatic number of 4. Let's look at a second example here. I'm not going to try to hide all this from you. I'm going to reveal it all. It's a very busy picture. I'm looking at the edge chromatic number of the complete bipartite graph K34. Okay. What does our theorem say? Well, the maximum degree, right, delta of K34 is 4. So we know that the edge chromatic number is at least that. The edge chromatic number of this graph K34 has to be at least 4. And while I claimed it equals 4, you can see I 4-colored it. I 4-edge colored it. And I just kind of want to walk you through a systematic way of doing this. So let me highlight so you're looking at the same thing I am. Let me pick a vertex, say vertex 1 here. You'll see I've got kind of an interesting index scheme happening. So I've got my K34, and I'm calling the index I the value that counts the indices, labels the indices in the smaller part. Okay, so 3 is less than 4. So I have an index I that goes from 1 to 3. And then these other vertices, instead of calling them like 1 to 4 or something, I'm calling them just 4, 5, 6, and 7. But I want you to think of it as the n plus 1, n plus 2, n plus 3, n plus 4. So that's how I get my labels. So I have these 2 indices. I goes from 1 to 3 in our example. And I've got an index j down here. J goes from 1 to 4. Sorry, didn't give myself enough room. And I think I just mispronounced which one was M. Here is my smaller one. So my M is 3, my N is 4. So don't trust what I say, trust what I wrote. All right. And in some sense, here's what I do. I take a vertex of degree 4. I've colored it pink. And I just randomly assign colors, okay? Color 1, 2, 3, 4. Call them red, blue, green, and yellow. All right, so can you imagine the graph? I've only colored the 4 edges incident with that vertex of degree 4, and I chose those colors randomly. I needed 4 distinct colors to do it. But then what I'm trying to show you is this so-called rotation scheme. I think you can kind of see it in the picture. As I moved over to vertex 2, I'm just kind of cyclically rotating the way I draw the colors to the other 4 vertices in the other part of the graph. So instead of going red, blue, green, yellow, when I move over to the second vertex, I cyclically permute them. So I go yellow, red, blue, green. Then move over to the next vertex, green, yellow, red, blue. I'm always keeping them in the same cyclic order. Yeah, if you drew those colors around a circle, they always go red, blue, green, yellow. It's just I'm starting with different ones. So that's what I mean by rotating those colors. All right. If you want to get kind of formal down here, if you know what I mean by congruence mod n, I can write down a recipe that's more mathematical in nature. So I've already explained my index scheme. I have an index I that goes from 1 to m, and I've got an index j that goes from 1 to n. Yeah. And when I want to make an edge between index I and index m plus j, the color I'm going to give it is j minus I minus 1, but I do that modulo n. okay? So for example, if I is 1, I minus 1 is 0, and so I'm just giving it color J. But the color is mod n, so I've got color 1, 2, 3, and 4. So that's how I colored the first vertex. Now when you let I be 2, well, 2 minus 1 is 1, so I'm going to give those vertices that emanate from 2, the ones that land in m plus j, I'm going to color them j minus 2. So if you start off with the value j equal 1, you might think, well, wait a minute, 1 minus 2, I is 2, so I minus 1 is 0. So 1 minus 1 is 0. And you can think, well, what color is color 0? I don't have a color 0. Well, I'm doing this mod n. So the color 0 is the same as the color 4. That's why I drew the yellow edge from 2 to 4. All right, so I think I'll just leave that here in the video lecture and we can talk about it in class. But if you kind of work through all of the indices, you'll see that that's kind of a systematic way of saying the cyclic rotation I was talking about. Okay, so your author in the book kind of gives fairly good proof of this fact in general. I have decided in this video lecture, I'm not going to, I think this illustrates what I mean by the rotation. I wrote out the recipe for any n and m. So in order to perform this, when you're given your complete bipartite graph, one of the values has to be less than or equal, and that's the one that you let the I range from. So this rotation scheme can be used to prove this theorem, that the edge chromatic number of a complete bipartite graph, k and m, it's just going to be the maximum of n and m. You know, it needs to be at least that. And I was just trying to give you an idea of how you could always realize an edge coloring with that number of colors. All right. So there's a theorem about edge coloring complete bipartite graphs. I think before we leave this graph, before I scroll, so I don't have to scroll back and make you nauseous, please notice that an edge coloring gives rise to matchings. All right, a matching in the graph, remember what a matching is, it's just a set of edges that no two of which are incident. So if you take all the edges of a given color, say like those 3 red ones, they form a matching. In this bipartite graph, it's not a perfect matching. You can't have a perfect matching in a non-equitable bipartite graph, but in any graph, not just bipartite graphs, if you have an edge coloring of it, then you have a bunch of matchings. You take all the edges of a given color. No two of those are incident, so they're a matching. Okay, so just kind of park that in the back of your brain for a second. So here is a little lemma I need. My next goal is I want to look at the edge chromatic number of complete graphs. And this is going to be a little step towards formulating that result. So let's suppose that we take a proper K edge coloring of some graph G. And then for each one of the colors, this is kind of a usual idea for us now from vertex coloring, I just let E sub I be those edges that get color I. Okay, I do that for every one of the colors. So I've got a proper K coloring. I let these E's, what I was just saying before is those, every one of those E sub I's is a matching. It's a matching in our graph. Okay, and the lemma says that the size of the graph, the number of edges, divided by the maximum size of those EIs, the biggest matching that comes from the K coloring, is never any more than K. Okay, let's try to prove it. Well, first of all, the edge set is partitioned into those E's. Yeah, no edge gets more than one color. Every edge gets a color. So if you add up the sizes of all the E's, you'll get the sizes of the graph. Okay, all those E's are certainly less than or equal to the biggest one. So I'm just writing that E1, for example, is less than or equal to the maximum. E2 is less than or equal to the maximum. They all are. And if you add that number, max EI, to itself K times, well, you get K times it. Now the lemma is proved by dividing both sides by this max. Yeah, it says that the size of the graph divided by the max is less than or equal to K. That's all the lemma said. Nice. Okay. So let me try to use that lemma to convince you that a complete graph with an odd number of vertices, so K2n minus 1, is 2n minus 1 colorable, and no less than that, that the edge chromatic number of it is 2n minus 1. This theorem, by the way, proves our baseball example was a minimal coloring. We had the graph K5, and we had a 5 coloring of it. According to this theorem, you can't 4-color that graph. So the minimal schedule for that Little League is 5 weeks long. Cool. Okay, so I'm going to borrow a notation from the lemma. I already said this. Each one of those EIs is a matching. It's a matching in the complete graph K2n minus 1. Okay, the size of K2n minus 1 is as big as it can possibly be. It's 2n minus 1 choose 2, which using the factorial formula is like that. And because 2n minus 2 is divisible by 2, I can simplify it. So there are 2n minus 1 times n minus 1 edges in the complete graph on an odd number of vertices. K2n minus 1. Okay. A maximum matching, you remember what that is? It's a matching with the most possible edges. Well, it's going to have exactly half the number, how to say that, because you have each vertex in K2n minus 1 is incident with 2n minus 2, that's an even number, other vertices. So a maximum matching would have exactly half that number of edges. So half of that number is n minus 1. A maximum matching in K2n minus 1 has n minus 1 edges. So if we run the lemma through there, we take the size of our complete graph divided by the size of a maximum matching, and we know that that's no more than k, where k is a proper edge coloring. Take any k edge coloring, proper k edge coloring of this graph, and that inequality would have to be true. Okay? So in particular then, if we take k to be the edge chromatic number, it has to be at least 2n minus 1. I'm certainly taking a little bit of algebraic liberty there and canceling that n minus 1 from the numerator and denominator. So that gives us a lower bound on the edge chromatic number. You're gonna properly edge color K2n minus 1. You need at least 2n minus 1 vertices. You can't do it with 2n minus 2. 2n minus 2 being the max vertex degree. All right. So now I just have to convince you that we can 2n minus 1 color it. Right? If I know that this is the minimum, and if I can achieve that, then I can say, well, then the edge chromatic number equals 2n minus 1. So that's what I'm going to try to convince you of. So let's label the vertices. Label the vertices of K2n minus 1 with just the numbers 1 to 2n minus 1. So you can kind of look at the leftmost picture over here. So I've got vertex 1, vertex 2, vertex 3, vertex n, vertex n minus 1. Or sorry, n plus 1, there's some dots, right? 3 dot to n, but then the next vertex would be n plus 1 dot, and I've labeled them the last two, 2n minus 1, 2n minus 2, excuse me, 2n minus 1. And leave the vertex 1 out. So there's 2n minus 2 vertices left. Pair them, and pair them like this. Connect vertex 2, the first vertex after 1 to the first vertex before it. The second vertex after 1 to the second vertex before it. That's going to pair up perfectly because I have an even number of vertices here. There's 2n minus 2 vertices there. Okay? So color those edges, color 1. Color 1 matches the index of the vertex that got left out. Okay, and now kind of a similar idea, although I'm not going to write it down in congruence classes this time. Rotate that picture. Just take that picture, leave out vertex 2 now. You leave out vertex 2, there are still 2n minus 2 other vertices. Pair them. Just pair them. First vertex after 2, first vertex before 2. Second vertex after 2, second vertex before 2, and so on. They'll pair up perfectly. Give that color 2. All right, keep doing that. Leave out vertex 3, leave out vertex 4. Go all the way around until you've left out the last vertex, and you'd be assigning those edges color 2n minus 1. Well, if you look at all of those edge sets together, you're going to get every single edge in the graph, K2n minus 1, because every edge incident with, or sorry, every vertex is incident with every other vertex, and we've just kind of paired them and indexed them as we went along, right? So this achieves a coloring of the graph. We know that no two vertices are incident with the same color because we're in any given color, we're just pairing a vertex with one other. So no two vertices get the same color, so it's a proper edge coloring of the complete graph. All right, so it takes at least 2n minus 1 colors. We did it with 2n minus 1 colors. That proves the theorem. I'm not going to do it here. I hope you don't think I'm lazy or avoiding you, but in a similar way, it's kind of a cool thing. You have to put, if you take a complete graph with 2n vertices, so an even, then you can kind of do the same argument, but you have to take the 2nth vertex and sort of put it in the middle, and then always give it a color that's sort of matching with the one that you are leaving out. Yeah. So if you do that for all of these things, that rotation scheme will end up 2n minus 1 coloring k2n. So you don't need an extra color. You can, if you have an even number, so you should try this. You should 5 edge color k6. K6 will admit a 5 edge coloring. Cool. So if our little league above got an extra team, sadly they would be called Team F. But if Team F joined our league, we could have everybody play everybody else, still playing 1 game a week, and we wouldn't need a 6th week. We could do it, and you can kind of go back to that example and see, you know, like if you had Team F. Can I scroll? Is it annoying if I scroll back up? If you had Team F join this league, well, okay, in week 1, have Team F play Team A. In week 2, have Team F play Team B, and so on. That's kind of what I mean by, you know, stick that Team F in the center and color accordingly. Nice. Okay. So I hope that was at least slightly illustrative of a couple of techniques, this kind of rotating idea. Now I just want to sort of end by listing some results. I'm not planning on proving any of these things. In fact, some of these things are not easy to prove. They require some technical notions that we have to kind of develop and prove lemmas about. And with just 6 lectures left in the class, I'm making the executive decision that I don't want to devote all that time to edge coloring. I've said this before, but this is a little bit more of a survey of many topics in graph theory course than it is rather going deep in any one topic. But I still hope you're getting a feeling for the spirit of the subject. Okay, so let's look at some known results. Wissing's theorem, proved in the 60s, says that the edge chromatic number of a graph is always at least the max vertex. We proved that. That's actually a trivial result. It's highly non-trivial that it's never any more than one more than that. Yeah, it's never any more than one more than that. So the edge chromatic number is always between the max vertex and the max vertex plus 1. That's a very small interval. Those two numbers differ by 1. So given a graph, its edge chromatic number, it's either the max vertex. I'll write this in a second when you'll see it. That's called class 1. If the edge chromatic number is the max vertex, it's called a class 1 graph. If it's one more than that, it's called class 2. And Wissing's theorem says that every graph is class 1 or class 2. It's an interesting result. Up here, we said that, well, let's notice that the max vertex of k2n minus 1 is 2n minus 2. Yeah, it's 2n minus 2. So that means that the complete graph on an odd number of vertices is class 2, that its edge chromatic number is 1 more than its max vertex degree. K2n has the same edge chromatic number, 2n minus 1, which happens to be its max vertex degree. So even complete graphs are class 1. So you can, both equalities are achieved in there. Here I have those definitions. So graph is class 1 if its edge chromatic number is delta G. It's class 2 if it's delta G plus 1. So just to write down up here, K2n minus 1 is class 2. K2n is class 1. Um, Koenig in the 1916s, so more than 100 years ago, proved that every bipartite graph is class. I mean, we have a proof that complete bipartite graphs are class 1. Koenig proved that every bipartite graph is class 1. Interesting. And then the last thing I want to mention, kind of bringing back this topic of complexity that I never fully understand, um, is that despite this teeny interval, that every graph has an edge chromatic number that's either delta G or delta G plus 1, it was proved by Hoyer in the 80s that algorithmically computing the edge chromatic number of a graph is an NP complete problem. So it's hard. It's hard to compute the edge chromatic number of an arbitrary graph, even though Vizing tells us it's basically one of two numbers. It's one of two numbers, the max vertex degree, but still algorithmically, it's hard to compute it. Okay, so there, I'm going to leave this here. I'm not going to try to include any more information here because I don't want this video to be unnecessarily long. But there's a lot of kind of open work in this business right now. So there are some necessary conditions for a graph to be class 1 that are conjectured to be sufficient, but nobody has proven that they're sufficient right now. So it's kind of an active area of research. I'm going to omit lists stating these conjectures because they typically get stated in terms of some technical things, the notions that we would have to define and develop about the graphs. And again, I don't want to take the time to do it in this survey course. All right, so if you can't come to the Zoom meeting, I hope that this was a decent kind of run through about some spirit of what edge coloring a graph is. And if you can come to the Zoom meeting, then we can talk about any of the details that you saw here, or I'll just try to recapitulate to the best of my ability what I tried to say here. Okay, thanks for listening.